In this explainer, we will be examining a framework known as MolDAIS, Adaptive Subspacing Bayesian Optimization for Data-Efficient Chemical Design. This is a framework designed to tackle a core challenge in chemistry and materials science, namely, how to efficiently discover molecules with optimal properties, especially when operating under conditions of data scarcity.
So here's how we'll break it down. We'll start with the molecular optimization challenge itself and the related problem of the representation bottleneck. Then we'll introduce MolDAIS and its concept of adaptive subspaces. After that, we'll review the empirical validation and performance benchmarks, followed by a look at its interpretability and use in multi-objective design. We'll finish up with conclusions and potential future directions.
All right, let's begin with Section 1, the Molecular Optimization Challenge. This is really about the difficulty of navigating what is a combinatorially vast chemical space.
So, what exactly is molecular property optimization, or MPO? You can think of it as a global optimization task. The objective is to identify molecules that possess optimal functional properties, starting from an enormous, high-dimensional chemical design space. And this isn't just an academic exercise. It's fundamental for advancements in everything from pharmaceuticals to new materials for energy storage.
And to give you a sense of the scale we're dealing with, a typical chemical library used for optimization can contain well over 100,000 candidate molecules. When you're facing numbers of this magnitude, trying to search through every single one to find the best candidate is, for all practical purposes, computationally intractable.
Now, it's not just the sheer number of molecules that's the problem. There are two major constraints. You have the combinatorial size of the search space, which we just noted, but equally important is the cost, both in time and resources, of actually acquiring the property data for any given molecule. Whether you're running a physical experiment or a complex simulation, it is expensive. So this all points to a pressing need for strategies that are sample efficient. We need a way to intelligently navigate this massive space using as little data as possible.
Okay, on to our second section, the representation bottleneck. The subtitle here, How a Molecule is Described Determines Optimization Success, really gets to the heart of the matter. The effectiveness of any data-driven optimization framework is critically dependent on how one chooses to represent a molecule in a numerical format.
When it comes to representing molecules, there are several common approaches. You can treat them as graphs, where atoms are nodes and bonds are edges. You can use string-based representations like smiles. There are also fingerprints, which encode the presence or absence of certain chemical substructures. And finally, you have descriptors, which are features based on physicochemical properties. The important thing to understand is that each of these methods comes with its own set of limitations, particularly in high-dimensional or low-data environments.
Broadly speaking, the field has pursued two main paradigms. On one side, you have fixed representations. These are handcrafted features like fingerprints or descriptors. The issue here is that they may not align well with the specific property you're trying to optimize, and their high dimensionality can be a challenge. On the other side, you have data-driven embeddings learned from models like variational autoencoders, but these also have drawbacks. They are often fixed after initial training, so they can't adapt as you acquire new data. Furthermore, the latent space they create might not be smooth with respect to the property you care about.
This all leads to an interesting question. What if the most effective approach isn't to invent a new representation from the ground up? What if, instead, we could intelligently select the most important features from a very comprehensive existing one? This idea of adaptively identifying relevant features from a large pre-computed library is the central hypothesis behind the MolDAIS framework.
And that brings us to Section 3, Introducing MolDAIS. The key idea here, as the subtitle suggests, is about learning which features matter.
So let's walk through how MolDAIS operates. It's a closed-loop process. First, you define your molecular search space. Then, you featurize every molecule in that space using a very large library of descriptors. Here's the crucial step. The system then imposes what's called a sparsity-inducing prior, a statistical method to learn a much smaller, compact, and relevant subspace from all those features. A Gaussian process surrogate model is then trained on only this important subspace. From there, an acquisition function selects the next best molecule to evaluate. And finally, that new data point is used to update the model and refine the subspace. This loop repeats, becoming more refined with each iteration.
The core mechanism that enables this is the Sparse Axis-Aligned Subspace prior, or SAAS prior. You can think of it as the statistical engine that performs the feature selection. Technically, it's a half-Cauchy prior placed over the inverse length scales of a Gaussian process kernel. What this means in practice is that it creates a strong preference for sparsity. It effectively forces the model to ignore most of the input features, paying attention only to a small, low-dimensional subspace that the data itself suggests is relevant.
Now, the fully Bayesian SAAS approach is the most robust, but it is also computationally demanding. To make the framework more practical, there are a couple of other variants. You have mutual information, or MI, screening, and maximal information coefficient, or MIC, screening. These are deterministic, low-cost methods that rank features. They offer less flexibility than the full Bayesian approach, but they provide a significant computational speedup, which can be valuable in practice.
So that's the theory. Let's move to Section 4 and look at the empirical validation and performance benchmarks. The question is, how does this framework actually perform in practice?
The first claim we'll examine is that MolDAIS demonstrates superior predictive accuracy and uncertainty calibration, specifically in these data-scarce regimes. To test this, the evaluation looks at the quality of the surrogate model on regression tasks using very small datasets, which simulates the conditions of early-stage discovery.
And the results are quite clear. This chart shows the test root mean squared error on the Gaussian benchmarks, using just 5% of the data for training. The MolDAIS bar consistently shows the lowest median error when compared to other methods representing fingerprint and graph-based approaches. This suggests its method of subspace identification is particularly well-suited for these low data settings.
Of course, for Bayesian optimization, predictive accuracy is only half the story. The model's uncertainty estimates must also be reliable. This table shows the uncertainty quantification analysis for a lipophilicity task. MolDAIS achieves a high R-squared value of 0.79 between its predicted variance and the observed error. This, along with a reasonable miscalibration area, indicates that the uncertainty estimates are well calibrated, and that is critical for guiding the search process efficiently. The next claim to investigate is that the identified subspace actually adapts and improves as more data is introduced. This is not a static, one-shot process, it's a dynamic one. We can see this process clearly on the free-solve dataset. When you start with just 10 training samples, the model's view on which features are important is very diffuse. But as you add more data, moving to 30 and then 60 samples, a clear, sparse subspace starts to take shape. By the time you reach 90 samples, the subspace is well-defined, and you see a corresponding jump in predictive performance, with the test set R-squared increasing to 0.84. So the model is accurate and it adapts. The third and perhaps most important claim is that this all leads to state-of-the-art sample efficiency in actual molecular property optimization tasks. Here we see the results on the penalized log-P task, which involves a search space of 250,000 molecules. The findings are noteworthy. The fully Bayesian version of MolDAIS was the only method that managed to find the globally optimal molecule in 100% of the 20 experimental replicates. The screening variants also performed extremely well, outperforming other established methods.
To put that performance into perspective, MolDAIS identified the optimal molecule after querying, on average, less than 0.04% of the total candidate search space. This means it located the top candidate after evaluating fewer than 100 molecules out of 250,000. This is a clear demonstration of its sample efficiency.
All right, let's move into our fifth section, interpretability and multi-objective design. Because beyond raw performance numbers, the framework also offers a way to gain physical insights and handle complex trade-offs.
Now, an important point here is that the quality of the scientific insights depends strongly on the starting descriptor library. When you use libraries like Mordred or PaDEL, which are essentially physics-inspired calculators that encode chemically meaningful features, the subspace that MolDAIS identifies can be scientifically interpreted.
And here's a concrete example. When tasked with predicting solvation-free energy, the model consistently selects descriptors related to polarizability and ionization potential. For instance, it identifies features that measure polarizability contrast between atoms or capture bond-level polarity. This aligns with the fundamental physical principles known to govern solvation.
The framework also shows flexibility in handling more complex problems. Take this multi-objective design task for organic electrode materials. Here, there are two competing objectives. You want to maximize the redox potential because that's related to energy density. But at the same time, you need to minimize the solvation-free energy, which is critical for the material's stability in an aqueous environment. And the results of this task are shown here. The chart displays the final log hypervolume, which is a key metric for evaluating the quality of the set of trade-off solutions, known as the Pareto front.
As you can see, the MolDAIS mix variant achieves a substantially higher hypervolume compared to a fingerprint-based method and random search. This indicates that it finds a better and more diverse set of solutions that balance the competing objectives.
This brings us to our final section, number 6, Conclusions and Future Directions, where we'll summarize the findings and look at what might come next.
So, to summarize the contributions, MolDAIS effectively combines large descriptor libraries with adaptive subspace identification. The result is a highly sample-efficient method for discovery, particularly in low data settings, where it consistently outperforms other common representation methods. Critically, when using physics-informed descriptors, the model is interpretable. Its modular nature also means it's extensible to more complex problems, like multi-objective optimization. Looking ahead, there are several interesting directions for future research. One idea is to account for correlated interactions between descriptors, perhaps using methods like kernel PCA. It would also be valuable to incorporate richer, more domain-specific descriptors, for example, features derived from quantum calculations for catalysis, and finally, a systematic evaluation of how well the framework generalizes across different core chemical scaffolds would be an important next step.
And this brings us to a final, thought-provoking question that this work raises. Does learning which known features are relevant, rather than trying to learn entirely new features from scratch, offer a more direct and interpretable path to accelerated molecular discovery? The results from MolDAIS suggest that, at least for data-scarce problems, the answer may be yes. It points towards a paradigm where we leverage our vast library of existing domain knowledge and then apply intelligent methods to select what's most relevant for the task at hand.